Welcome to virtual algebra class. Today we're going to be talking about slope as a rate of change. We do have a GED student with us today, Miss Marilli, but she's been having some technical issues. Hopefully she can get back into class, but we will get going now here. So slope as a rate of change. Why do I want to talk about this? Well, the deal is that slope can come up in word problems, and a lot of times they won't use the word slope. You know, they do that to us in word problems all the time. They give us a real life scenario and we're just supposed to recognize what we're finding. And so slope shows up in word problems a lot. And when it does, sometimes they'll say find the slope, but most of the time they'll use rate of change language. So you need to realize that these two concepts are synonymous. So this is how it's going to show up in real world problems or application problems. A lot of my students are not math majors. They're going to end up going to college for not math subjects. And so they're going to take a sequence of math classes that are designed for people who are not necessarily math people. And you'll see slope most often as a word problem or an application problem in these kind of classes as well, not just on the GED, because they figure if you have a real world thing to think about, it's going to be easier for you. Okay, so we do need to recognize a slope problem this way. So I will remind you that slope is a rate of change. The other way we talked about it was your rise over your run, okay? Rise over run. So we've talked about slope a lot of different ways in the last two classes. But today we have got to introduce this idea. Last way we talked about it. It's your change in y. That's your rise, your change in y over your change in x, your run, your vertical change over your horizontal change. And hopefully that's Marilli back. Hi, Marilli. I just started a little bit. You barely missed anything, but we'll keep going from here. Okay, so I was looking at three different ways we look at slope, right? Slope is a rate of change. It's the rise over run. It's the change in y over the change in x. We've talked about all these things already. But today, we're going to see slope. Another way to think of slope is as a rate of change. How fast the independent variable is changing over the dependent variable changing. Oh, I just actually made that wrong. The dependent over the independent. Sorry. So now let's take a look at some problems here. Okay. So we're going to start with some stuff we kind of already know, but we're going to look at it in a real world setting, okay? So this first example I want to do asks a few different questions about this graph over here on the right. So example 1 says the following represents the graph for a helium balloon's flight. And we see this graph here with two variables. We've got time and we've got height. And one thing you should know is that as mathematicians, we almost always use the x axis, the horizontal axis, to represent the independent variable. So this down here, the time, is our independent variable. Time marches on no matter what I do. It's independent. Time just moves on by itself. That's one of the ways I remember it. And usually time, very frequently, the independent variable is time. You're going to see time a lot on these graphs when you have real world applications, because we're often looking with a line graph about how things change over time. Does that make sense to you, Miss Marilli?
Yes.
Now, the vertical axis, or we also call it the y-axis, is where we use the dependent variable. So what we're seeing here is that the height is going to depend on time, and that makes sense. Over time, the height of my balloon is changing. It's going up over time. So my height depends on the time. It's the dependent variable. Does that make sense to you?
Yes.
Great. So A says, determine the rate of change of the graph. And so all I want to point out to you is that rate of change is absolutely synonymous with the word slope. They mean the exact same thing. So I'm not learning something new here. I'm just thinking about something I've already learned in a new way. It's how fast my balloon is rising over time, the rate of change. And so I'm really just looking for the slope of the graph here. So this graph's really, really nice because I start at 0. So it's going to be super easy to count my rise over run. So I think I'll just go from this point to this point. And if you missed how to do slope on a graph, you should go back to the intro to slope video. But I'm going to rise from 0 to 1,000. I just rose 1,000. Over how much time? Well, that was just 1 second from 0 to 1. So over the course of 1 second, I went 1,000. Over the course of 1 second, I went 1,000 feet. I went 1,000 feet in the course of 1 second. That means that my slope, my rate of change, is 1,000. But 1,000 what? You're actually going to write down these units. 1,000 feet per second. And notice that I use a slash for per. Do you see that slash? That's the same symbol I use for divide. And we've talked a lot about how per and divide mean the same thing. And that's going to come up a ton today. Okay, so I'm saying I'm raising 1,000 feet per second. Every single second, this balloon's going up another 1,000 feet. Does that make sense to you?
Yes.
So that's all I mean by question B. Could question B show up on the GED? It sure could. It would probably be a multiple choice if it did. But it says, what does this slope or rate of change mean? It means my balloon goes up 1,000 feet every second. That's a really quickly rising balloon. Oh, it's not the second, is it? Do you see? Look at what I did wrong. Do you see it? Look at the graph. It says time is in minutes. I'm super slow. Sorry. It should have been 1,000 feet per minute up here. And my balloon goes up. Now that makes more sense. I was like, dear goodness, this balloon is going up fast. 1,000 feet each second. That's what that slope means to us in real terms. Does that make sense to you?
Yes.
Okay, great. So next question says, when is the balloon at 5,000 feet? Show this at your graph, on your graph. So here's my 5,000 feet. So I'm just going to go over horizontally over to my graph. And I can see that it hit 5,000 feet at 5 seconds. Or 5, I keep doing that.
5 minutes.
5 minutes. Thank you, Really, keep me in line. Okay, cool. So then, Marley, would you be able to figure out how high the balloon is off the ground at 2 seconds? Or 2 seconds. Woo, that's harder than I thought it was. Let's do 2 minutes, okay? I actually didn't write this graph, this worksheet, but we'll do 2 minutes. So how high is the balloon off the ground at 2 minutes?
2,000?
Absolutely 2,000 feet. 2 seconds, it wouldn't be very far off the ground at all. No, because it'd be way back here. I don't even know. Okay, now this is an interesting question. It says, although not on the graph, when will the balloon reach 10,000 feet? And they ask us to show our reasoning. 10,000 feet. Well, we've only gotten up to 6,000 feet at 6 minutes. Any ideas?
Double the 5,000?
Oh, that's so smart. That is so smart. You're saying, well, if in 5 seconds I got to 5,000, double that would be 10,000. So then it would take me how many minutes?
10 minutes?
I don't know how many times I'm going to say seconds in this video, but it's very humiliating. Okay, in 10 minutes. Brilliant, Marley. Thank you. So we can see that these graphs can be used for really practical purposes, okay? That's all I wanted to point out. Is it a line and some points? It is a line and some points, but it's also very practical information. So let's take a look now here at Brady's savings account. So this graph, it says the following represents the balance in Brady's savings account. First thing they ask us to do is find the slope of the graph. Once again, finding my slope is going to be pretty simple, but I'm not starting at 0, 0 here, so I really am going to have to think about how much I'm going up. So I think I'll go from here to here. Are you cool with that? Mm-hmm. So if I go from here and I go up, how much up did I just go if I went from 300 to 500?
2 minutes? 2 months?
Oh yeah, but I was going up first. So look at the vertical axis, the number
500.
of dollars. I just went up from 300 to 500. So how many dollars did I go up?
500.
I ended at 500, but I started at 300. So how much of a change is that to go from 300 to 500?
Oh, sorry, 200?
Yeah, 200. So that's a really important concept on a graph. You're looking at change. When
Oh,
we started at 0, it was super easy to see the change because we just had to go up to 1,000 from 0. But here we started at 300. It was a little trickier to see that the change from 300 to 500, I went up by 200. Does that make sense?
yes.
Good. So I rose 200. And then now, yeah, you can tell me how much I ran. I did $200 over how long?
2 months.
2 months. And that one did start at 0, so it's super easy to see. So $200 over 2 months means that my slope is 200 divided by 2, which of course would be $100 per month. Does that make sense?
Yes.
Slope of this graph is $100 per month. So then question B says, what does the slope represent as a rate of change? What does that mean to us if the slope is 100 here? What's happening to his bank account? Is it going up or going down?
It's going up.
Okay. By how much each month?
100.
Exactly. That's the idea there. It's going up 100 each month. Does that make sense?
Yes.
That's that idea of slope as a rate of change. So now this is an interesting question. It says, how much did Brady deposit when he opened the account? How much? What did he say?
300.
300. Brilliant. How'd you know that?
Because it starts in.
Because it starts at 300. Your y-intercept or your starting point absolutely is 300. Right, and right there we can see that at month 0, at our starting point, we were at $300. That's where our graph started. Wonderful. And it says, at this rate, how much money will Brady have in his account after 15 months? After 15 months. So right now we're only up to
12 months.
12 months. And how much did you tell me it was going up each month?
100.
100. So at 12 months, we've got $1,500. So where would I be at 13 months?
At 6.
Absolutely, $1,600. And at 14 months?
17.
$1,700. So how about at 15 months?
18.
18. Brilliant. Nice. Is this pretty simple, these applications of graphs?
Yes.
Yeah? Okay, so let's look at them when they're just straight up word problems, no graph. That can be harder for us to realize that it's the same kind of problem. Okay, the GED has both very, very simple rate of change word problems, and it has more complex ones. But I feel lucky because a lot of subjects on the GED are never simple. They go straight to the complex problems. Rate of change or slope problems are one of those where they do have lots of simple problems. So we can pick up a lot of easy points that way. So let's look at example 3. It's a really simple problem. It says, over the course of 5 hours, the temperature in Prescott, Arizona, dropped 32 degrees. What was the rate of change in degrees per hour? I want to increase there. Is that easier to read?
Yes.
Okay, sorry.
That's fine.
Okay. So notice that they asked me, what was the rate of change? And I'm so pleased because I know rate of change means slope. But I'm so pleased because not only do they tell me this is a slope problem, they tell me how to find slope. Students don't realize that they're actually giving you a map to do the problem right here in this phrasing. Look what they said. They said in degrees per hour. I cheer when anybody tells me to find something per something because they told me exactly what to do. They're telling me to take the change in degrees. Well, how many degrees did my temperature change by? Look back at that problem. How many degrees does it say my temperature changed by?
32, drop 32.
It dropped 32. See that language, dropped 32? Think about what we learned about signed numbers. If it dropped 32, that's actually a negative 32. Does that make sense?
Yeah.
Okay, so we have this drop of negative 32, and then it says per. That word per, we use a slash to abbreviate per because it literally means divide. We are going to divide negative 32. And what are we going to divide it by? Well, we're going to divide it by the number of hours. Degrees per hour means take the degrees and divide by the hours. So how many hours did it take for it to drop that much?
5 hours.
5 hours. This problem literally says take negative 32 and divide by 5. And you and I know that you'll have your TI 30XS whenever you do a word problem on the GED. So you can do the division here. The important thing is to keep the order the same. The divide by button on your calculator, divide by, means exactly the same as a slash. So keep your order the same. The biggest mistake students do is reverse the numbers. Okay, so I'll put in negative 32, I'll divide by 5, and I get negative 6.4. So my temperature is dropping negative 6.4 degrees per hour. And notice how my answer has 2 units in it. It's degrees per hour. Rates of change or slope is always a something per something. Does that make sense?
Yes.
Okay, so negative 6.4 degrees per hour. Brilliant. Okay, number 4 is another one of those super simple examples. A bunch of 7 bananas, cost Jolene $2.73. How much did she pay per banana? How much did she pay per banana? Right there, it tells me exactly what to do. I'm going to take how much she paid. So how much did she pay, Marilee?
273.
Exactly. Her pay was $2.73. And I'm going to per it. And we said per means divide. By the number of bananas. How many bananas did this woman buy?
7.
7. See how simple these problems can be?
Yeah.
So 273, and I'm going to remember to go in the exact order. I'm also going to include my decimal point. Some students leave it out, and then they get charged really a lot of money for their bananas. And I get this number out of my calculator. What does this mean to me?
39 per banana.
Exactly. I'm 39 cents or 39 hundredths of a dollar per banana. We don't usually say hundredths of a dollar, do we? We usually say 39 cents. But yes, 39 cents a banana. Okay, wonderful. So we can see that these slope or rate of change problems can be super simple on the GED. I cheer when they're like this. Okay, it's wonderful. But it could get more complex. So let's take a look here at these more complex problems. Okay. Number 5 says at 4 this afternoon, the temperature was 73 degrees Fahrenheit. So once again, I'm talking about temperature and time. By midnight, it had dropped to 45 degrees. What was the rate of change in degrees per hour? So they're still asking me to find a rate of change. They're still asking me to find slope. They're still telling me in degrees per hour. So where I'm going is the same, but the kind of information I've been given is different from the last problem. In number 3, they told me how much the temperature changed. And they told me how much the time changed. But here, they don't tell me how much the temperature changed and how much the time changed. I'm going to have to do the work to figure out the change in the degrees. And this should look a lot like a slope problem now. And it really is a slope problem. Over the change in the hours or time. Okay, so I can see that originally the temperature was 73 degrees, and now it went down to 45 degrees. Marilee, how could I figure out how much the temperature changed?
Divide 73.
Well, I'll divide to find the slope, but I don't have that yet. I need the change first. So let's think about this. So hold on a second, because we actually did this last class, but I don't know if I made a clear link to it. So remember when I told you if I weighed 220 pounds and then I lost weight and I went down to 180, right? So we talked about that last class. We said, okay, if Kate had weighed 220 pounds and now she weighs 180, how would I figure out how much my weight changed? Well, I know all of us females know how to figure that out, right? How much did my weight change by if I started at 220 and went down to 180?
You minus?
Exactly, I'm minus. So if you have to find the change, if it wasn't given to you, you're going to have to do some minusing before you can deal with the slope. Does that make sense?
Yeah.
So if I started at 73 and I went to 45 degrees, how much did I change by? I'll take the new temperature, 45, and minus the old temperature, 73. So I'll take my new degrees and I'll minus my old degrees. That's always how you find change. And you could use your slope formula for this too. It'll tell you the same thing, y2 minus y1. But the tricky thing is, it's like, which one's y? A lot of students don't know. Okay, but I'll do my new temperature minus my old temperature, and I'll get negative 28 degrees on top. Does that make sense?
Yes.
So tell me why my temperature is negative. Why do you think my change is negative of my degrees?
Because it has dropped.
Exactly, my temperature dropped. So even if you subtracted in an opposite order, I would expect you to realize, oh, hey, my temperature dropped, it went down 28 degrees. Mm-hmm. Brilliant. Now let's think about our change in hours. Well, my first temperature that I measured was at 4 o'clock this afternoon. This second temperature I measured at what time?
At 4.
That was the first one. The first one I measured at 4.
Oh.
What time did I say I measured the second temperature, the 45 degrees?
At midnight.
At midnight. At midnight. So what's my change of time? How much time has passed from 4 in the afternoon to midnight?
8 hours.
8 hours. Brilliant. You can take that midnight, that 12, the new one, and you can subtract that old one, that 4 o'clock, and you would find that was 8 hours have passed. Very nice. And so now I can do my division. I can divide my change in temperature by my change in time. And I would get negative 3.5. So that's negative 3.5 what? Degrees per hour. And see how it can get more complex if they don't tell you your change? So if they give you starting points and ending points, you'll have to subtract to find your change. Does that make sense?
Mm-hmm.
Okay, so let's try one more. I got another one like that. Example 6, it says Jenny's subtotal at the grocery store was $14.95. But then the grocery clerk rang up her bananas. So here I am buying bananas again. The subtotal after ringing up the bananas was $16.80. How much did she pay per banana? Okay, so we're looking at how much she paid per banana. Pay per banana. But again, I have a tricky thing because this money numbers that they give me, they didn't tell me how much she paid for the bananas. Instead, they give me a starting price and an ending price before and after bananas. Can you see that?
Yes.
So I have a change in the subtotal. Merle, can you help me figure out how much I actually paid for the bananas using the two subtotals that I had? What would I do with those two numbers?
Minus them?
Exactly. So I'll take my new number. So my most recent number is 1680. And then from that, I'll subtract my old number, 14.95. Oh, I'll write down my work that I'm doing so you guys can have it in your notes. I'm taking 1680 and subtracting 1495. That's what I'm doing on top. And I'm doing it in my TI-30XS calculator. And I'm finding out it cost me $1.85. Now, it cost me $1.85 for how many bananas?
5.
Yes, this one was a straightforward number. They just told us it was 5 bananas. Mm-hmm. Okay, so I'll divide the 185 by my 5 bananas. And I find out it cost me 37 cents or 37 hundredths of a dollar, but 37 cents per banana. Is that cool? You see how it got a little tricky?
Yes.
Okay. Let's go on. I've got a couple of even trickier examples. Can I move on from this page, my dear?
Yes.
Now, I have seen problems like number 7, example 7, a lot on the GED. where they're straightforward, but it's a little confusing which is your independent variable and which is your dependent variable. So let's take a look. Jonah is a car salesman who receives a monthly salary plus a bonus for each car he sells. In a month where he sells 10 cars, he makes $9,400. In a month where he only sells 4 cars, he makes $6,400. If you were to graph his earnings, what would be the slope of the line? So at least on this one, they were kind about reminding us that this is slope. But the tricky thing here is they don't tell us blank per blank. So we don't know which thing should go on top and which thing should go on the bottom. And so let's look at the two kinds of numbers we're looking at. Some of the numbers that we're looking at, like the 10 and the 4, represent a number of cars. And some of the numbers that we're talking about, the 9,400 and the 6,400, represent the number of
Earnings.
dollars, exactly, his earnings. And so sometimes it helps students to think, you know, of a graph. That's one way that students will do this better, to realize which is the independent and the dependent variable, because they know that the independent variable, the thing that marches on by itself, is usually that horizontal movement, and the dependent variable, the thing that depends on the other, is usually the vertical axis. So I think about this, you know, what depends on the other thing? Well, the money that this man makes depends on how many cars he sells. So the money would go here. It would be the result on my graph, whereas the cars would be there. That's the thing that his money depends on. Does that make sense to you?
Yes.
Okay, so knowing that, when you go to do your slope, it's always dependent variable over independent variable. So I'm going to be finding the dollar he makes per car. I'm going to be finding the dollars per car. That'll be the slope. And that makes more sense than finding the car per dollar. Because it'd be a really tiny little piece of a car per dollar. That doesn't even make sense. Like, how many cars do I sell per dollar? Not many. Does that make sense? So
Yes.
dollars per car make a whole lot more sense, okay? So dollars per car. So let's figure this out. We're going to need the change in his dollars over the change in his cars. So let's look at the change in his dollars, okay? Well, if he had $9,400 sometimes, but then other times he has $6,400, I could just do change in dollars that way, subtracting that way. It's like I have 2 points. When he sells 10 cars, he makes 9,400. So like the point 9,410. And when he sells 4 cars, he makes 6,400. So like the point 4,6400. Okay, so I'm going to subtract those two numbers. Now, we said it doesn't matter which one you choose as 0.1 and 0.2, which order you subtract in. We learned that last video, as long as you keep your order straight. So if I subtracted my y's like that, I'd be doing my x's like this. So to do my change in cars, I'll start with the $10, the one that's paired up with 9,400. And then from that, I'll subtract the 4 cars, the one that's paired up with the 6,400. We can see my order's the same. Does that make sense to you?
Yeah.
Cool. So how much did my dollars go up based on selling more cars? Well, 9,400 minus 6,400 means that he had a change in his earnings of $3,000. Okay? And by the way, when I do this, I'm actually plugging into the slope formula. I have it memorized. I forgot to explicitly tell that to you guys. Change in y over change in x. And then on the bottom, the change in the number of cars he sold was a change of 6 cars. And now I can do my division now that I have my change. So 3,000 divided by 6 would be 500. So help me make sense of this number. This is 500 what per what, Marily?
$500 per car.
Exactly. So the slope of this line would be 500 because this man is making $500 per car for every car he sells. Is that cool?
Yes.
Okay, awesome. So then number 8, and this is our last one. So short class today, yay. A climber, because I talked so long last time, I did the video and I was like, really, Kate? You like 15 minutes before you even got to a problem. I felt sorry for you all. Okay. A climber is hiking up a mountain. After 2 hours, he is at an altitude of 1,200 feet. After 4 hours, he has at an altitude of 1,360 feet. What is his average rate of change? So they told us rate of change. So we have to just remember that means the same as slope. So it'll be our change of our dependent variable over our change of our independent variable. But the trick here is figuring out which one's which one goes on the top. That's really the hardest part of this problem. I have to think, does it make more sense to do hours per foot or feet per hour? And that's a hard decision. And I'll help you remember that I usually put time on the x-axis, the horizontal axis, because time is usually independent. It just marches on whatever I do, okay? So do you see the time in this problem?
2 hours.
Exactly. So my hours will be my independent variable. And then what depends on the time? What's my dependent variable? What was that?
Altitude.
Altitude. Brilliant. So I have my altitude, how high I'm at, depending on how long I've been hiking. And I think that makes sense. So I will make sure that my altitude goes on top. I'm going to do rise over run. So I'll do my change of altitude. Over my change in time, which makes sense. Feet per hour makes a lot more sense than hours per foot. Okay, I'll do my feet per hour. So let's see, how much did my altitude change, Marily? How could I figure that out?
Let me see. Sorry, I'm confused.
No, that's okay. Let's look at our two altitude numbers. So I have an altitude here of 1,360 feet, and I have an altitude here of 1,200 feet. So I started at 1,200 feet and I went up to 1,360 feet. So to figure out how much I changed, how could I do that? Do you remember what math operation will give me change?
Minus.
Exactly. I'll take my new one, 1,360. I'll subtract my old one, 1,200. So it reflects the fact that I'm going up. So that would, of course, be 160. But let's deal with my change of hours. So how many hours was I traveling here? How much time went by as I hiked in these two scenarios?
160.
Oh, you're telling me in minutes, aren't you? You can keep it in hours. How many hours change was it from 2 hours to 4 hours?
Oh, 2 hours.
Yeah, exactly. 2 hours. And that's a really common issue that students have, by the way, Marily. You're not the only one. We automatically want to try to convert hours into minutes. We don't need to unless it tells us to. Okay, so 2 hours. Okay, so I went 160. Oh, I actually want to erase that. You did it right. I just want my notes to be good for everybody. So what Marily did here was she said, well, if I ended at 4 hours, come on, pen. And I started at 2 hours, 4 minus 2 would be 2 hours traveling. Okay, great. So I went 160 feet over the course of 2 hours. I'll divide that through, and that's 80 feet per hour. That's how fast I'm rising. Okay. Or how fast my altitude is changing. My altitude is changing at a rate of 80 feet per hour. That is the rate of change. Cool. So these problems can be tricky. Like I said, the trickiest thing is figuring out which one goes on the top and which one goes on the bottom. But I have some exercises that you can try with them so that you can practice that. Again, some really good clues is time is usually on the bottom of slope, okay? If you have time, that's a real obvious one. Just slip that on the bottom. It's usually the independent variable. Okay. Any questions about any of this, Miss Marily?
No.
No, then you're out of jail free. All done. We are good for today. Next time we get together, we are going to be looking at slope from an equation. So we've seen slope on a graph now. We've learned how to find slope when you have 2 points. Now, today we saw slope in word problems. So last, we're going to see slope in mathematical equations. And then finally, we're going to attack the kind of GED problems where they compare the different forms of slope. And that can be really tricky for students because it's hard when you have to do the same problem in different ways, all within the same GED example would be really tricky. And so I'm trying to build up to that level, okay?
Okay.